said, one of the really important pieces of information
I get no kick from champagne.
How these things break up can give us information about their structure.
Mere alcohol.
So for instance, if I inject 2-methyl-pentane like this into my instrument, some of it might survive without fragmenting. It would only lose the 1 electron. So my mass to charge ratio, this M over Z, mass to charge ratio, would be sort of 86 divided by 1 charge. So we'd see a peak at 86. Let's think about some ways that this could break down to give me radicals and cations from this radical cation. So these are a couple ways that I could fragment this. Again, this is a radical cation. It's short in electron. And so we can kind of think of one of these bonds as actually being a half bond that I'm going to break to give a cation and a radical. Right? So I could break it to give this cation and that radical. I could break it to give that cation and so forth. Okay? But some of these are more common and more important than others, because of what we've learned about cations, right? So the more substituted a cation is, the more stable it is. And so in this case, the more stable a cation is, the more likely we are to see it. So for instance, these secondary cations are probably the best that we can do here. But what we're not going to see is any kind of methyl cation. That's out, right? So that's really, really unstable. And so we're probably not going to see a whole lot of a big peak at 15. In the same way, it's probably not that likely that we're going to get a peak at 29 either, because this is a primary cation, right? So here I would expect my bigger peaks to be there and there, or maybe even, or I might even see loss of hydrogen atom to give me this tert-butyl cation at 85. So here's what this data looks like coming out of the mass spectrometer. We see the tiny little peak for the actual molecule itself at 86. Very, very small, what we call an M-1 peak. The biggest peak here is M-43. If you remember, that is sort of the we call the 3-propyl cation from before. We also see a pretty big peak here at 71. We said that was probably from the one where it lost a methyl group at this 2 position there. Smaller peaks abound. You can kind of tie yourselves in. You can tie yourself into knots trying to pin down every single little peak in a mass spectrum. So it's really important to be able to figure out what the base peak is. The base peak being what's this biggest peak, and can I make sense of it? But also we'd be looking for really commonly showing up peaks too. M-15 is almost always loss of a methyl group. M-29 is loss of an ethyl group. That's pretty common too. But this is what a mass spectrum looks like. Here we go. Test yourself. Here is propylbenzene. What do you think the most stable cation we can make from this is? So break a bond to get a stable cation. What bond is going to break? Well, you might think it's going to be this one, but remember, I don't want charge on the ring. I want it charged next to the ring. That charge is delocalized throughout the ring, and so we will see a giant peak at 91. That will be by far the tallest peak in the mass spectrum. Far and away, the biggest peak in this mass spectrum is going to be the peak at 91, because that cation in the benzyl cation is very well delocalized into the pi network. Right? So that's going to be the most important fragment we see from this mass spectrum. Okay, so you can teach a whole class in fragmentation of mass spectra. A lot of this was discovered by Fred McLafferty at Cornell, who is still at Cornell when I was there, so I got to hear him talk and got to be around him. Really, really cool old guy with colored suspenders, just kind of walking around saying, I don't know organic chemistry, but I know how to add. This is all adding. McLafferty was a great guy. Still alive, 90-something years old. Anyways, the one way that these things fragment that I want to teach is what happens when there's an oxygen or a nitrogen around, or a heteroatom. Again, a heteroatom is essentially not carbon, not hydrogen. And so the idea here is called alpha cleavage. So it's simply that when I look at my atom, if I have a ketone like this, I'm going to draw it like this. The alpha carbon is the one next to the carbonyl, and I'm going to cut there. Right? So if I cut there, I get this methyl radical, and I get this cation, and the cation is actually delocalized. Even though it doesn't look like it, I can pull a lone pair from this oxygen over. And so that's a relatively stabilized cation. And so we'll see a mass loss of 15 here, big peak in acetone's mass spectrum at 43. If we're looking at asymmetrical ketones like this, we can manage cutting them on both sides, right? Not at the same time, but some of them, we'll see some peaks that get cut on the left, and so they give us a cation at 99. We'll see another peak at 57 for those molecules where we fragmented on the right instead, right? And so these will be two pretty big peaks in the mass spectrum. Now they might keep breaking down from there, but we should definitely see these two peaks. We've seen it for cations. Does it apply to aldehydes? It does, but only one way. So if I have an aldehyde like this, I can imagine losing just that hydrogen atom. So we might call this an M-1 peak. It'd be one less than the mass. So if I take the mass spectrum of a benzaldehyde like this, I'll see a peak at 106, and actually I'll also see a pretty big peak at 105. However, I'm not going to see a peak that's just for CHO like that, because that just breaks down too quickly to carbon monoxide and an acid proton. So won't see the formal cation, not a thing, but if I see an M-1 peak, I right away start thinking about maybe it's an aldehyde. Although it looks a little bit different, we can see the exact same thing happen with alcohols. So here, even if I don't have that pi bond here, I'm going to draw my alcohol so it sort of looks like a ketone, and I'm going to make the same chops, because this lone pair on oxygen can still help stabilize a cation next to it, like that, right? On both sides of that. So we learned earlier that lone pairs can help stabilize cations. So this is a consequence of that, is when I take the mass spectrum of an alcohol like this, if I can be able to chop on another side and see stabilized cations like that. One last example here, same with amines. So if I have an amine like this, I'm going to be able to break at that carbon so that I can get to a cation next to that nitrogen atom. That nitrogen can stabilize that cation with its lone pair. And so we see the same kind of alpha cleavage for amines as we do for alcohols and ketones.